Everyone knows that a compass points us towards the North Pole. It's a bit of knowledge you pick up when you're growing up and it's very easy to understand. But it's not quite as simple as it might seem. Hi, I'm Grant and welcome to the 5th class in the GNAV series. Today we're going to be looking at direction and how it isn't quite as simple as just north, east, south and west. The Earth has a magnetic field formed mainly by the molten iron core in the centre of the Earth. This core has a life of its own and it's liquid, so annoyingly it doesn't create a magnetic field that lines up perfectly with the true north and south poles. It is slightly offset and actually changes year to year, day to day. An easy way to think of it is as if there was a giant stereotypical magnet straight through the Earth at an angle like this, and the magnetic field comes out of the south field and around and back in to the north magnetic pole as so. It is important to note that a compass will always point towards the magnetic north pole. So if we were standing directly on top of the magnetic north pole, our compass would be pulled all the way down and it would try to stand up vertically. Conversely, when we are at the magnetic equator, this kind of imaginary line at the halfway point of this magnet, then there would be no force pulling us down and the compass would spin perfectly flat and point towards the magnetic north pole. Essentially, what I'm trying to say is there's a vertical and horizontal component to the magnetic force experienced by the compass. The horizontal component is the component that spins the compass round, and it is known as the directive force. So you can imagine if you're looking at a compass from a side-on angle, it would be the one that kind of spins it this way. This is what we're seeing down here. This is the sideways angle, and it's just going to spin the compass. And then there's also the vertical component known as magnetic dip. And as you get further and further towards the magnetic north pole, you get more and more dip and the compass becomes less and less able to spin. And at a certain point, when we are very close to the magnetic north pole, you can find that the horizontal component of this magnetic force is so weak and the magnetic dip is so high that a compass actually becomes unusable. So because the true North Pole and magnetic North Pole are not aligned, it means that there is a certain amount of inaccuracy when using a compass. The compass aligns itself with magnetic north using the directive force for that position that we are standing in, and the true north is always at that point very at the top of the Earth. So if we measure a magnetic bearing, there would be a difference between it and the true bearing. The difference between the two is known as variation. And depending on where you are in the Earth, variation is either east or west. In this example, it is east, which we consider to be positive variation because the magnetic north is to the east of true north. So while our true bearing is about 90 degrees, our magnetic bearing would only be from the magnetic north, and it would be this angle in here, which is about 80 degrees. And you put a little M to signify magnetic or a T to signify true. We can use a simple equation to convert between magnetic and true north. So the easiest way is doing magnetic plus variation equals true. And remembering that east is positive and west is negative. And then you can do a simple error check using a little phrase. You basically say if the variation is east, the magnetic will be least. If the variation is west, the magnetic will be best, as in the higher number or the lower number. When we're using our compass to navigate using magnetic directions, which is common for most regions of the Earth apart from very close to those magnetic poles where the dip is too high to be able to use compasses, then there is often an error in the compass. This error comes around because planes are metal basically, and they've got lots of electric and moving parts, so they generate their own magnetic fields when they're powered up. So we have to account for this error or the aircraft would point us in slightly the wrong direction. This difference is known as deviation, and it works very similarly to variation. So basically we have a compass north, which we give this little C arrow to, and that is pointing to a different north than our magnetic north. And just like variation, we can use a simple equation to convert between one and the other. So what we say is compass plus deviation equals magnetic, with the same rules where east is positive and west is negative. So for this example here, we can see that the west variation here means it's negative. So we could do our compass, which we don't know, plus the deviation would be minus 10 equals the magnetic, which is 90. Then we would take it over and it would be a heading of 100, which, as you can see from our diagram, makes sense. And again, you can use that simple tool to error check. If the deviation is least, the compass will be least, and if the deviation is west, the compass will be best, as in the higher number. To figure out the deviation of an aircraft compass, a process known as compass swinging is carried out, where an aircraft is lined up with known magnetic directions and the reading on the compass is compared. The difference is then noted down and you create a table which looks like this, but probably a bit neater and more tidy. So you would say for 000 for a heading of north, you need to steer 001. For a heading of east, 090, you would need to steer 089. This is typical. The differences are only ever a few degrees off, but a few degrees off over long distances makes a huge difference. So we can combine the concepts of variation and deviation together, and the best way to do this is through this little example that I've shown. So if the true bearing of an aircraft is 305 degrees true, deviation is 3 degrees west, and variation is 7 degrees east, what is the compass bearing? So for once, and probably the only time in GNav, I'm going to tell you to don't bother drawing a picture. These equations are actually easier these examples are actually easier if you just use the equation. So we can combine the two equations that we've just seen together. So we know that compass plus deviation equals the magnetic, and then the magnetic plus variation equals true. An easy way to remember this is that it's C, D, M, V, T. And the way that I was taught to remember this is there's a type of chocolate bar here in the UK called a Cadbury's Dairy Milk, or chocolate dairy milk, I suppose you could call it. So Cadbury's Dairy Milk, very tasty, CDMVT. That way you can remember the order. And then you just plug in the numbers that we've got here, remembering that east is positive and west is negative. So we're looking for the compass, so we're going to leave that as a C. Deviation is 3 degrees west, so that's going to be plus minus 3. I suppose I could have just written minus 3. Equals the magnetic, which we don't know, plus the variation, which is 7 degrees east. East is positive, equals the true, which is 305. And then we would find out our magnetic. So our magnetic in this case equals, we take 7 away from 305 and get 298 plus 7 equals 305. That makes sense. And then we have to take away 3 from our compass to get to this. So our compass would be 301. And then you can just error check that. So 301 minus 3 equals 298. Yep. 298 plus 7 equals 305. That's correct. So our compass bearing is 301 degrees, and then you give it a little C for compass instead of magnetic or true. And then you could error check it again with that magnetic least and compass least sort of check. So if the variation is west, which it isn't, sorry, if the variation is east, the magnetic is least compared to the true, yep. If the deviation is west, the compass is best. So compass is best compared to the magnetic. And you get a final answer, which we've already discussed. So another level of complication can be added through wind. So let's say we have the aircraft, this aircraft here pointed fully true north and we're traveling straight up a meridian. If we have wind from the right, then we would be pushed off course as we travel along unless we correct for it. In this example, we would have to point the aircraft to the right, and as we fly along, the wind would push us and we'd keep flying along the correct track. This is the difference between heading and track. Where the aircraft is pointed, that is our heading, and where the aircraft is traveling, that is our track. And the difference between them, if we didn't correct for it, would be called a wind drift angle, and when we do correct for it, would be called a wind correction angle. So in this example, our heading and our track are the same, but that would push us off course. So I'm going to draw it what it would look like corrected. So as you can see, our heading would have to be into the wind by a wind correction angle. And the wind drift angle would only exist if we didn't correct for this. And the wind drift angle will be completely opposite to the wind correction angle. You only really have one or the other. So for this example, while our track might be true north, our heading is maybe 010 degrees true, because our wind drift is 10 degrees to the west. So that would mean that our wind correction angle is 10 degrees to the east. And that would mean that we maintain a track of 000 degrees true, or true north. So in summary then, the Earth has a magnetic field which is offset and constantly changing because of the molten core. The easiest way to think of it is this: if you've got this bar magnet through the top and the Earth's magnetic field projects out and around from south to north, as so. This magnetic field is also offset from true north and true south. A compass lines up with these local lines of the magnetic field, so it means that we get something known as magnetic dip when we get close to the poles. And at high latitudes, the dip can be so severe that it means that the directive force isn't strong enough to actually pull the compass around and give us any useful information. This is sort of a side-on view. So at high latitudes, you'd be looking at it side on and it'd be dipping down so much that the directive force wouldn't be too strong. And then at low latitudes, aka like the equator, then you have a lot of directive force and very little dip, so they're actually more effective. Because of this offset of the magnetic poles, it means we get something known as variation, because the true north and magnetic north are in different points, and depending on where you are on the Earth, that means that you get a difference between the two, and it could be as extreme as 180 degrees. If you were standing in between the two, magnetic north could technically be behind you whilst true north is right in front of you. And then you also have an error in the compasses that we use caused by the aircraft themselves. And the easiest way to think of all of these things combined together is with Cadbury's Dairy Milk Very Tasty, Chocolate Dairy Milk Very Tasty, some other acronym to remember. And it's compass plus the deviation equals the magnetic, and then you plus the variation, and that equals the true. Remembering that east is positive and west is negative. And then you can do those error checks where if the variation is east, the magnetic would be least. If the variation is west, the magnetic would be best. Or if the deviation is east, the compass would be least. If the deviation is west, the compass would be best. Then we can add a further complication to it by talking about heading and track. Heading, think of it as where the aircraft nose is pointing. Track is where we're actually traveling. And the reason there's a difference between the two is because of the wind. If we didn't correct for it, we would drift off course by a drift angle. And if we invert that drift angle and steer into the wind, that's known as our wind correction angle, and that allows us to stay on the desired